In our previous presentation, we understood what is big O notation, and with the help of an example, we learned how big O notation is helpful. It helps in describing the performance of an algorithm with respect to the input size. In other words, it tells the growth rate of an algorithm. We took an example of linear search. In the last lecture, we observed that the growth rate of linear search is linear with respect to the input size. This means the growth rate of linear search is big O of n. And this means as the size of the input increases, the running time of linear search increases with the same rate. That's why the growth is linear. Now in this lecture, we will try to describe the growth rate of binary search, and that too using the big O notation. So the title of this lecture is Big O Notation and Binary Search. Let's get started with this lecture and let's see what are the topics. The first topic of this lecture is Big O Notation and Binary Search. The second topic is Growth Rate of Binary Search. And the third topic is Growth Rate Comparison of Linear Search and Binary Search. Let's get started with the first topic, which is Big O notation and binary search. In case of linear search, we know that we compare each element of the list with the key which we want to find. But in case of binary search, we do not do this. In binary search, every time half of the list is eliminated, this means we do not compare each element of the list with the key. Instead, we every time compare the middle of the list with the key. Therefore, the number of comparisons in case of binary search is less than that of the linear search. Let's draw the table of number of items and number of comparisons in case of binary search. Let's say that the number of items is 10. In binary search, the number of comparisons will be 4. If we have 100 items, then the number of comparisons will be 7. If we have 1 billion items, then the number of comparisons will be just 30. What if we have n items? What will be the number of comparisons? Is it n? No. We can observe that number of items is not directly proportional to number of comparisons. If we have 10 items, then the number of comparisons is 4. If we have 100 items, then the number of comparisons is 7. If we have 1 billion items, then the number of comparisons is 30. What about n? What will be the number of comparisons in this case? This is not as straightforward as linear search. In order to determine the number of comparisons, here, if we have n items, then we need to do some calculation. We know that in binary search, every time we divide the list by half, this means every time half of the list is eliminated. Let's take 100 items. We know in the second stage, we will be left with 50 items. After this, we will be left with 25 items. Then we will be left with 12 items. Then 6 items. Then 3 items. And finally, 1 item. And the number of comparisons will be 7. The number of comparisons is equal to the number of boxes we see here. There are 7 boxes, therefore the number of comparisons is 7. So when we have 100 items, number of comparisons will be maximum to maximum 7. Now what if we take n items? In the second stage, we will be left with n by 2 items. Just like in case of 100 items, we will be left with 50 items in the second stage. Similarly, when we have n items, in the second stage, we will be left with n by 2 items. We need to divide the list by half. Or, in other words, we will be left with half of the list, which is n by 2. What happens in the third stage? We will be left with n by 2 square items. Because, again, we need to divide the list by half. In the fourth stage, we will be left with n by 2 to the power 3 items. And this will continue up to n by 2 to the power of k. This we know is equal to 1 because at the end we will be left with one item. So n by 2 to the power k items is equal to 1. How many boxes do we have here? We want to determine the number of comparisons or the number of operations binary search takes. In order to know this, we need to know how many boxes we have here. Here we have n by 2 to the power 0 items. Here we have n by 2 to the power 1 items. Here we have n by 2 to the power 2 items, and so on up to n by 2 to the power k items. This means we have a total of k plus 1 boxes. K boxes from here to here and one extra box here. So a total of k plus 1 boxes. We are assuming k is some constant, but we don't know its value yet. Up to this point we know we have k plus 1 boxes. And k plus 1 boxes means we need k plus 1 comparisons in case of binary search when we have n items. So there are k plus 1 comparisons. To simplify the calculation, let us assume that we just need k comparisons. In place of k plus 1, now we need k comparisons. This is just for the simplification of the calculation. So now we want to know the value of k, because we eventually want to know how many comparisons binary search takes in case of n items. How do we find the value of k? We know n by 2 to the power k is equal to 1. We just need to solve this equality. Let's do this. N by 2 to the power k is equal to 1. This implies n is equal to 2 to the power k, or 2 to the power k is equal to n. We just need to multiply 2 to the power k on both sides, and we will get 2 to the power k equal to n. Now let's apply log on both sides. I am assuming that you already know the basics of logarithm. By applying log on both sides, we will get log 2 to the power k base 2 equal to log n base 2. I am applying log base 2 on both sides here. That is why we are getting log 2 to the power k base 2 here in the left hand side and log n base 2 on the right hand side of the equality. Now let's solve this. Log 2 to the power k base 2 is k. So this implies k is equal to log n base 2. And what is k? K represents the number of comparisons or the number of operations. So the number of comparisons is log n base 2, and hence the running time of this algorithm, which is binary search, is big O of log n. I mentioned earlier that big O notation tells the running time as the number of operations. This log n represents the number of operations, and this is not the precise value. We know we need k plus 1 comparisons. So this must be log n base 2 plus 1. But we are not considering that plus 1 because again we are just estimating the running time. We do not have to worry about the constants. Hence we can say running time is big O of log n. Even I haven't mentioned base 2 here. This is also not important. What is important is that the growth rate of binary search is logarithmic. This means as the size of the input increases, the number of operations increases logarithmically. So the growth rate is logarithmic. I hope this concept is clear. So running time of binary search is big O of log n. These many operations binary search takes to come to the conclusion whether the key is available in the list of n items or not. So in case of n items, the running time is big O of log n. So this means we can replace question mark by log n, and hence the running time is big O of log n. So with this we calculated the growth rate of binary search. Now let's visualize the running time through the graph. For this, let's move to the next topic where we will visualize the growth rate of binary search. This is how the growth rate of binary search looks like. The growth is logarithmic. Here I have plotted these points, and I got these points from this table. Here I have plotted this graph using this table. When number of items is 10, the number of comparisons is 4. When number of items is 100, the number of comparisons is 7. When number of items is 1 million, the number of comparisons is 20. When number of items is 1 billion, the number of comparisons is 30. The growth rate is logarithmic. This means as the size of the input increases, the running time does not increase drastically. Hence, binary search is faster than the linear search, because in case of linear search, we got linear growth. In order to properly visualize the growth rates of linear search and binary search, let's move to the next topic where we will now compare the growth rates of linear search and binary search. These are the graphical representations of growth rates of linear search and binary search. In case of linear search, the growth is linear. In case of binary search, the growth is logarithmic. Here I have mentioned the time complexities or the running times of linear search and binary search. In case of linear search, the time complexity is big O of n. In case of binary search, the time complexity is big O of log n. We can observe that linear search is slower than binary search, as the growth rate is much faster in case of linear search compared to the binary search. So with this, we are done with this topic also, that is growth rate comparison of linear search and binary search, and this means we are done with this lecture. Okay friends, this is it for now. Thank you for watching this presentation. I will see you in the next one.